Okay, there you go. Still alive?
No.
Don't think so. No, sorry.
Okay, well,
First, again, welcome everybody, and so we have Gary Yu, if I'm not mistaken, from Denso Corporation, is that right?
Yes, yeah.
Okay, we'll be talking about condensation and evaporation. So,
Okay, thank you. Sorry about my late appearance. My name is Gary. I'm working for this master as a senior in developers. And today I'm going to present the work we have been doing for some time regarding the modeling of flow condensation and the boiling used for.
oh, sorry, sure. Yeah, I'll do it.
Okay, I'll do this. Yeah, okay.
Or you can move it there if you like.
No, that's okay. That's here. Okay.
Whatever you.
Yeah.
Okay.
Does it work?
I think you have to maybe click here first. Yeah.
Okay.
And yeah.
Right. The company was founded in 1984, and later in 1989, it was a member of the Basic Corporation. It's a Japanese company, and it's based in West Yorkshire, England. The company designs and manufactures engine cooling modules for all highway heavy-duty vehicles like tractors, diggers, evacuators, or any agricultural machines. So these are some of the images of the cooling modules made by the company. Some backgrounds. Why do we need to develop CFD solver for simulating the phase change process? Because to accurately simulate phase change process is a very, very important step to optimal design of the phase change heat exchangers. As shown by this image at the bottom left, it is a water-cooled condenser used in heat pump system of electrical vehicles. Now, when we design this type of heat exchanger, before making prototype, we have to do one simulation to predict its performance regarding the heat transfer rate, pressure drop on both film sides. So since currently there is no mature CFD tools available, so we have to rely on experimental data for heat transfer and pressure drop in the numerical simulation. And most of the time, these correlations are not accurate or applicable for new complex phase geometries as shown by this small image here. It's very complicated geometries. So also showing in this table, you can see the difference between the simulation and the test on the refrigerator side pressure drop. It's very big. The predict pressure drop on refrigerator side is more than half smaller than the test. So therefore, we need a CFD solver to simulate phase change process, especially when we design a new type of fluid passage. So we use WARP method for two-phase flow simulation with phase change. You can see from the right-hand side of these three equations, there is a term called m dot. This represents the mass transfer rate due to the phase change. We need this model to calculate this mass transfer rate. So this table summarizes three most popular physical model used in CFD code. For the energy jump model, interface reconstruction algorithm is required in order to calculate the interface area. So another prerequisite for using this model is that in the domain, there must be interfaces available. Otherwise, the solver or this model cannot start phase change simulation from a single phase domain. So the issues for these two models are very similar. Because there are two model coefficients here and one here. They all require preset values. These values are normally not known in our experimental data. From our experience with this model, either you give value for this model is still depends on the mesh size and boundary condition. So we decided to go for energy jump model because this model doesn't require any preset model coefficients. There are further assumptions for using this energy jump phase change model. For example, for the condensation, the vapor phase is treated as saturated, and the liquid phase is subcooled. So the phase change heat transfer rate is calculated by the heat conduction on the liquid side only. So for the boiling process, the liquid phase is treated as saturated, and the vapor phase is superheated. Therefore, the heat transfer rate due to the evaporation or boiling is calculated only on the vapor side. So as I mentioned in the previous slide, interface reconstruction algorithm is required for this model. So in the code, we have to define a pointer to the reconstruction scheme as shown in this alpha liquid dictionary. This scheme, the detail of this scheme can be found from this paper. The last barrier for using of this model is to make sure it can start the phase change simulation from a single phase domain. Most of the cases, the initial condition we normally set is pure single phase. For example, if the domain is filled purely by saturated liquid or saturated vapor, so the model cannot automatically start the simulation. Since there is no phase change, so even use this construction algorithm, there is no phase change, the phase change area is zero. So we have to assume dummy cells on the outside of the wall, then this wet itself will be treated as the interface area. Then you can have this model kickstart the phase change process. Oh. No. Okay. Oh, sorry. Yeah. We have run several cases using this code for the code validation purpose. We started from modeling the stable evaporation program. This is a typical or classical test case for phase change code validation. There is an analytical solution for this interface location and control time. And in our case, we started from simulation like this. This is the wall, which is superheated, and on the right hand side is saturated liquid. Because this wall is superheated, then the condensation of evaporation will immediately start from this side and gradually evolves and layers the wall over it. And in this figure, we plot the interface location for alpha liquid equals 0.25 and 0.50. And the red solid line represents the analytical solution. You can see the code predicts the trend very accurately. I would say this is not an ideal test case for validating the warp method. Because in warp method, there is no sharp interface between liquid and gas. It's not from 0 to 1. There is a transition between 0 and 1. So you don't know exactly the location of that interface. So in this case, I use 0.5. People may argue why don't you use 0.75. So we can't get any definite really in terms of code validation. So we have to so just play this with you. I don't know why it doesn't play automatically. Huh? What could you play this? All the animation. It's just a short clip showing all the. Oops. This one works, but okay, never mind. Okay, so just forget about the first one. Okay. Yeah. Okay. So as I said, we need to properly validate the code. In other words, we need to positively validate the code based on either theory or test. So for the evaluation code, we use film volume process. So there are these are the 4 correlations published in this paper for the film volume process. It's claimed in the paper that the acidity of this correlation is plus or minus 0.5. For a phase change correlation, this is pretty good. And you can see all the test points scattered around the center correlation line and between the top and bottom limits. So in order to compare with the test, we have to use the same characteristic length scale for the new self-number calculation as before. And we also need to use the same temperature difference for the calculation of heat transfer division. And we average the heat flux on the bottom wall, which is super heated, and then calculate the heat transfer coefficient and then the self-number. This slide shows the cases we studied for laminar film boiling. And as shown in this two tables, you can see all these non-dimensional variables are very different. So making two very distinct two cases. And from this table and also from the previous slide, you can see the correlation between CFD and the test is quite good. And CFD is about 7% lower than the test. So for the turbulence volume, we also studied two cases. So this time we only vary the beta value. Beta represents the ratio between the latent heat and the central heat. So different beta value corresponds to different correct function. You can see F20 is different in these two tables. So for the first case, we have very good agreement between the CFD and the test. And for the second case, the CFD is about 11% lower than the test. But considering the 25 minus plus 25 acidity, this is also acceptable because for this case, we use small mesh die. Sorry, number of mesh cells is more than half of the margins in Evaporation, which saves simulation time, is acceptable for us from engineering simulation point of view. It takes this one, the second one took about 4 days on 32 CPUs. It's okay. It's interesting simulation. I talked about the time step limit for this kind of simulation. Going for the condensation code validation, we studied the film condensation on a vertical plate. For this case, Nusselt theory gives the film thickness variation along the wall and also the heat flux around the wall. So in the CF estimation, we monitor the average alpha liquid fraction in the domain. When the state like that was reached, we stop simulation and we take the time average solution, for example, from this point to the end of simulation, we for the post processing process. This figure plots the film thickness for CFD with alpha liquid equal 0.5 and for the Nusselt film. And on the right hand side is the plot for the wall flux. About 6 millimeters from the top of the wall, the equilibrium is really good. And after that, you can see the film is thinner than the theory. This is because in cell theory, the film is assumed to be stable. But in reality, putting the bottom of the domain, the film is really to the pattern. So therefore, we enhance heat transfer rate, and you can see the heat flux. In this case, it's about 10% higher than the theory from CFD. Okay, I'm going, okay. Another case we studied film condensation on the horizontal tube. The first thing we found that the OpenFOAM built-in surface tension force model doesn't work for micro scales, and a different surface tension force model based on sharp interface was implemented for micro scales. So I'm showing this based on this paper, and I'm showing these images. The left one shows the liquid profile at time instant 1.8 seconds. From this time onwards, this figure in the middle shows the film image or film profile with the OpenFOAM surface tension model, and this one shows the profile with the newly developed surface tension model. So you can see the one in the middle has almost destroyed the film, so it means that it works properly. And for this case, there is no cell filter, also average local variant, but it's sufficient, and the CFD accordingly only predicts the heat transfer, and more simulations are therefore required. And at the moment, the time step for using this model is very, very small, makes it not practically useful for engineering simulation, especially on complex geographies or large domains as well. So, in order to make them more attractive for engineers, for engineering simulation, further work required to reduce the time step, to increase the time step 5, for example, 21-5 or 21-4, even better. And one thing I have to think of is to use sub-cycles for the solution of the energy equation, using a relatively large time step for pressure equation. So to conclude my presentation, energy change model was implemented in OpenFOAM, which the model doesn't require a preset model coefficient or coefficients, but it is increased reconstruction. A sharp surface tension model was implemented in OpenFOAM for close at micro scales. The code was validated for film condensation and evaporation process as well. So the time step must be very small in order to use this physical model. Further development is required to increase this time step size, make it useful for engineering applications. So I really hope anyone in from this audience, either in this room or attending the workshop remotely, could contact me if you are interested in the work I have been doing, and I'm especially interested in the discussion with the multi-cycles of energy efficiency. So I left my address here. Okay, thank you very much.
Awesome.
Thank you.
Thank you.
For the questions.
Thank you for your presentation. I saw that you work in industry, but I saw that your simulations are simulating like 1 or 2 seconds. What would be the applicability of your model for example, if you wanted to simulate something that takes hours?
Right, it's the thing, for the boiling, for example, for the boiling, film boiling, the very truth, there is a critical length skill called Taylor lead length, which above this scale, the film boiler is active. So when you do the simulation, you have a transition period from the initial condition. After a short period, it's totally active, it's fully turbulent, or even lambda flow is still active. Then you don't need to run a much long time, the solution will oscillate all the time, and so it's not the working. Yeah, this is the reason, yeah. So you can see for the turbulent flow, the simulation time is very short, so 1 second, but for lambda film boiler, it takes much longer to reach the stable state.
And the fact to use a real solver, real solver instead.
No, we have, I think this is the next step. This.
As for using for that application.
Yeah, the only because we studied this project 1 time ago. So the first OpenFOAM in the foundation and the evaporation So, but only.
That was my question. What's the difference?
Oh, that's why the response is appear for this storage development. But probably that's always the phase change physical model is it's the least model, which is also used to be active.
Okay.
But in Star, it doesn't even have this feature. So for the least model, I have another slide I'm not sure here. The show different model coefficients given to the model leads to different results. So you don't do the model different values beforehand. So you just find an error, but it's very hard to do because in practice the time is also going to work. I think somebody needs to be public paper try to adjust the issue based on the local energy conservation law to multi-cycle the energy efficient in this strategic moment scale. This is not practically useful for us data because we can't for random simulation for 4 or 6 weeks. We need the results quickly for engineering.
Okay. Well, thanks again. We have a very tight schedule, so we have to move on. Please,
Thank you very much.
Okay, so next speaker is NIKOLAS, SCURO, please. We will talk about some progress on two-way coupling on OpenFOAM between OpenFOAM and THERMOCHIMICA for volatility processes, right?
Thank you.
Chemical reactions.
Yeah, sure, because I have to finish. Right. Good morning, everyone. My name is NIKOLAS SCURO. I'm a PhD candidate at Ontario Tech University in Canada. And today I'm going to present the progress on two-way coupling on OpenFOAM and THERMOCHIMICA for fluoride volatility processes in molten salt reactor applications. I know that it might be a little bit offset from the major of the topics being presented here at this conference, but I'll do my best to show you what it's about. The outline of today's presentation is why molten salt reactors and also what is molten salt reactors, the objective of my presentation, which also the objective of my PhD thesis, what is and how I implemented a two-way coupling between these two libraries, some aspects of verification and validation, conclusions, and acknowledgements. First, I need to introduce you about molten salt reactors. I don't know if there's anyone familiar with nuclear field here, the nuclear energy? Awesome, thank you. So just for those who are not familiar, imagine that we have like a giant pool of molten salt. This liquid is generating fission and then producing like fission products, and a lot of things is going on there. But I just want to let you know that industry is a lot of interest in developing molten salt reactors, as it might be a good solution for generation 4 nuclear reactors. It may not produce as much nuclear waste as it's been generating right now, and it might be more efficient. These are some examples of companies that have been developing molten salt reactor. So this is quite a reason enough to study this application. And what I need to do, so as I was telling here, this is a very simplified model of a molten salt reactor. So imagine that I have a liquid and it's flowing, and the liquid is generating heat because we are having fission inside of it. And at the same time, this liquid is not something as simple as water. So this is a mixture of several different things that it's melted, and the composition is changing along the time. So it's more or less half of the periodic table flowing together and changing and generating heat. And it may also a three-phase flow, a mixture of liquid, gas, and gases. So it's a very complex problem. So we need to study the fluid transport. On one side, we have temperature, velocity, what we normally simulate using computational fluid dynamics. But at the same time, we have something more, as complex as it is for computational fluid dynamics, we have the fluid chemistry. So we have to understand the chemistry of the fluid that is flowing. So we need to understand which species are flowing and what phases and what is the chemical equilibrium of that composition. Under the chemistry side, we may say phases and different end states. So liquid, gas, and solid are 3 different states, but for each state, you may have different phases. So, for example, we have different liquids flowing together. We normally in the chemistry side say that there are different species flowing together into the same state. For that, we have computational thermodynamics, which can calculate the chemical equilibrium of this chemistry side, and then we can use that to use as chemical reactions. And for the nuclear field, this is a novelty when you are coupling both fields together for molten salt reactor applications. So the objective of my thesis will be the developing of a new computational capability for phase transformation and chemically reacting dynamic flows involving molten salts. And the main reason why we need to simulate that is to help design an integral experiment on molten salt reactors. It's really complex to develop experiments involving that. So to have a numerical tool set that may provide some capabilities of that, it may save a lot of money for industry already. And we need to understand the sensitivity between thermophysical properties for these chemically reacting dynamic flows. And at the same time, as I said, we need to create this tool set that may be able to simulate, to accomplish the first and second objective, which can also be used later to simulate accident scenarios. So we don't want the reactor to explode. So we need to simulate that to understand the consequences and how to avoid those situations. And it's better to do that numerically. And so what I'm going to do, as I said, I'm going to couple computational fluid dynamics using OpenFOAM, and these will provide inputs to the computational thermodynamics library that will return inputs to the computational fluid dynamics side using THERMOCHIMICA library that I'll explain in the next few slides. But to calculate all these chemistry calculations, we need to use a specific chemistry database. And for my PhD, I will use the JRC molten salt database. The JRC, it's an institute here in Europe from the European Commission that develops research towards molten salts. That I'll explain later too. I need to state here that this is not a predictive tool for industry yet, but I hope in the future it might be to develop such capabilities. So for those who are not familiar, THERMOCHIMICA is a chemical equilibrium library based on a Gibbs energy minimization. It's also a really complex topic to discuss here. So the main thing that I need to explain to you is, for those who are not familiar, it's more or less like chemistry calculator. So let's suppose you have carbon and you have oxygen. What's going to happen for under temperature and pressure? Oh, you might form CO2 and CO or CO3. So this is the kind of calculation that this library does. And we can apply that for molten salts. And we just need a few inputs like temperature, pressure, the element mass that you're wanting to calculate. For molten salt, it's a list of elements, but it could be, as I said here, an oxygen to form something I think called CO2. But we need a database, the thermodynamic functions to calculate that, otherwise it's impossible. Then THERMOCHIMICA will minimize the energy of all possible species that may form, and then I will have the molar phases, the species of mole fractions, and way more. So heat capacity, enthalpy, and many other properties that may be available to be used. So these are the outputs. Then what is the JRC molten salt database? As I said, this is a chemistry database where I provide thermodynamic functions. So just to introduce you here, for example, you can imagine the temperature and pressure map of water. Oh, at a certain pressure at 100 degrees C, I will boil water. And then if I change the pressure, I have a different boiling point, etc., or different temperatures. It's more or less the same, but when you apply that for different species. So if I have sodium iodide and lithium fluoride, if I mix both at a certain proportion, when at certain temperature, I will have like a solid phase or a liquid phase or a gaseous phase. And we do that in a laboratory using a glove box. This is me at Ontario Tech University, where we perform several different mixtures of those salts, and then we put into a machine, and then we analyze when it's gonna melt. And then we can create these phase diagrams here to better understand when certain species will melt and, or solidify, or when we have a mixture of several different phases. So the objective here, I will explain to you a very simplified demonstration problem when I couple both codes using a molten salt system. As I said, it's a mixture of several different species flowing together. So imagine that we have a molten salt system with 5 different species. So we have lithium fluoride, zirconium tetrachloride, thorium, beryllium, and uranium. So these 3 phases will be our coolant, and those 2 will be our nuclear fuel. But during the process of the molten salt reactor, we may clean the salt. We need to clean the salt. Because after some fission, after some operation on the reactor, we need to recover the nuclear fuel, clean up the salt, and then return the nuclear fuel again. So to recover the UF4, our fuel here, one of the processes that you can do to recover that is to vaporize UF4 injecting fluorine. It's a very reactive gas, and it will attach to UF4, and then it will vaporize UF4, forming UF6, uranium hexafluoride. Then this is a very complex chemical process. It's just summarized here in a very simplified way. But basically, we are injecting a gas into a liquid to recover one species of the liquid into a gas. And why I choose this specific problem to simulate? Basically, because we have experiments to compare and then have a better sense if my coupling would be correct or not, or at least in the path to be correct. To get started on my coupling, I started with multi-phase OpenFOAM version 9. This is a very simplified fluxogram of the algorithm. Just to state here, I just needed to use this solver because it matches a lot of necessary requirements for my simulation, and also the solution of the species transport equation was also available. Then THERMOCHIMICA was coupled right before the solution of the species transport equation. And THERMOCHIMICA, as I said, is an equilibrium calculation. So let's suppose we have a cell here with half liquid and half gas. If something on the gas side is reactive to the liquid side, I instantaneously will update the mass fraction of the species and then progress the solution. So basically, I'm updating the mass fractions according to the THERMOCHIMICA's inputs. So if something was under the liquid side, for example, the UF4, THERMOCHIMICA will tell me, hey, you have some fluorine here. So you are vaporizing that UF4, and then now it's not UF4 anymore, it's UF6. But you also have some UF4 remaining. So you didn't vaporize all the content. Then, just to let you know, this is the aspect of the experiment made by a Chinese group at Shanghai. The same was used, but for a crucible, sealed into a very specific laboratory facility. This is a representation made by myself at Ontario Tech University using water and gas and air. But the dimensions here, from the pipe, from the mass flow rate of the gas, from the size of the glass, they're all the same used from the experimental side, but applied for water and gas. I just wanted to analyze the bubbling effects and how different that would be from a American simulation that I did for my application. I know they're different. I know that we have all the theory behind our previous presentation here, but that was the most affordable simulation due to the complexity of the species transport, and then of course that should be improved in the future. But so far it was enough for a preliminary simulation. So as I said, we are going to vaporize UF4 to UF6. Here is a very simplified, oops. It's not working. Can I minimize the presentation just to show? Let me try. So the previous animation here was what you saw. So we have the injection of fluorine from the bottom to the top. And here is our here are the mass fractions counter plot from fluorine. As you can see here, I have higher concentration of fluorine from the bottom, and then less concentration to the upward. And then it's the inverse analyzing the UF6 content, because basically the salt here that has UF4, the UF4 is being vaporized. I am using the fluorine to form UF6. I could have shown here the same counter plot for the liquid state, for the liquid species, but as the decreasing of UF4 is so small along the time that it was more useful to show the gaseous species here. But the same is occurring for the liquid species.
1 minute, Nicholas.
Okay. Then I could compare the removal of UF4 along the time. The experiment took 3 hours to fluorinate all UF4 contents. And in green, you have my solution for my two-way coupling. And then in blue, you have the experimental answer. And the most differences here are due to the fact that I'm using equilibrium. I'm not assuming chemical kinetics. I have a lack of chemical and temperature-dependent thermophysical properties. I have a lack of fission products database because the experiment also used irradiated fuel salt. So way more chemical species was involved into that, and I had to simplify. And we always have uncertainties from the experimental side. Here is a comparison between lower viscosity and higher viscosity and how that changed from the simulation side. So as you can see here, we have a perfect column of gas from lower concentration viscosity, and when we increase the viscosity, it becomes harder to inject the gas. That reduces the area, and then the mass fraction of UF4 decreases. UF6 decreases. That's why we increased the time for that much. So we could correlate both the fluid transport and chemistry side for the fluorination process. I will not have time to talk about the verification. But all thermochemical calculations was verified through a commercial code that can calculate the same calculations. And I followed the best practices from OECD NEA for the multi-phase flow simulations. And in conclusion here, I was able to provide a two-way coupling of molten salt reactor application involving different thermophysical properties on the chemistry side. But I know that in the future that need to be validated with integral experiments. And then once that it's done, I will simulate real application next in scenarios involving a real power reactor. I would like to acknowledge the Canada researchers, the SEMO-SAFER project, and colleagues for technical discussions. And I'll be more than happy to answer any questions. Thank you.
Thank you.
Preference. We have let's go for the neutrons. Sorry, I couldn't get your question. Can you repeat? Well, in your real case, you did an experiment with nuclear fuel.
The experiment was not being radiated at the time it was done. So it was a solid, it wasn't radiated, and then it stopped in radiation, and then it was fluoridated. Of course, we have the decay, where we have several different decay products, the decay of other different products. So that was matter experimentally, but I'm not taking that into consideration because I don't have all of the species available from that. So when you have an account of your then late. I need to take that under consideration because I'm not because I think it happened at the university. But more in the area analysis part, the reference part goes up. So, I made it by hand, to be honest. THERMOCHIMICA is a Fortran 70 code, and then we have an API to call the Fortran functions from the C++ side, so that I could couple that within OpenFOAM under the memory level. So I don't know if I answered the questions, but yes, it's made line by line, very carry.
And also, how about the interface, like the model? Because I know to get multiple, to get all that form is pretty tough because you have a bunch of models that you. So does THERMOCHIMICA take care also of some of the parameters that you need to perform the modeling within interface all that form?
No, THERMOCHIMICA is just providing me what the next fractions should be.
Okay.
So all the rest will be taken by OpenFOAM. But for this simulation, it doesn't look like some circumstantial, drag, lift, etc. I tested many different parameters to try to match the best fluid flow. That's the best I can do. Okay.
Okay, thanks.
Thank you.
Okay, so our last speaker is Andrea Sartirana, right? That will be talking about multiscale multi-region framework to simulate dynamic operating condition of a treatment system for automotive applications, right? So
Yeah.
Catalyzer kind of thing? Catalyzer kind of thing?
Yeah, we got it.
Okay, thank you.
Okay, it's not good. So, good morning, everybody. My name is Andrea Sartirana, and I'm a research fellow at the Internal Combustion Engine Group of Politecnico in Milano. So today I will present our work that is named MULTISCALE MULTIREGION framework to simulate dynamic operating condition of after treatment system for automotive applications. So let's start from the motivation that brings us to develop the TLT methodology to simulate the after treatment system. So the main reason is tightening trend of the regulation and the levels of admitted pollutant emission that brings to increasing development cost for the design of the new after treatment system. So in need of a detailed description of the thermal transit of the components and also of the pollutant species conversion. So now let's start to have a look more in detail in the computational framework. So the simulation relies on a quantitative transfer and mid-duration approach, where the catalytic substrates are modeled as porous media. So for this reason, there are overlapping domains, such as the fluid and the substrate, and they are coupled by proper coupling models. So microscale simulations are necessary to characterize the properties of the properties of the porous media, which is viewed on the macro scale. So here there is an overview of the Vernon equation of different domains that are considered, namely fluid, solid, and substrate domain. So there is the possibility to consider more than one substrate domain. For example, the electrolytic catalyst is a generic substrate with the integration of an electrical field. Here there is also the possibility to see what are the different coupling terms that are used to coupling different regions. So Now let's pass to the difference of models that we have implemented to simulate the substrate. So, as I have already said, the substrate are simulated as a porous medium, and in general, the characteristic dimension of the grid is larger than the typical length scale of the channel substrate, and for this reason, the subgrid geometry model is required to characterize the geometrical parameters of the catalyst. So the names that are used in the simulation are the surface volume ratio, the target diameter of the single channel, the characteristic size of the solid structure, and the wash cut thickness. So to consider the free dynamic resistance that is encountered by the fluid when it's going through the channel of the catalyst, the permeability model was implemented, and there are several correlations that permits to calculate the source dams integrated in the momentum equation of the fluid. And here reported the two main used correlations, which are the Arlen-Quezel and the Darcy-Gardner correlation. So the interface heat transfer model instead model the heat exchange by convection with the gas and the walls of the channel. In the same manner, is modeled the interface mass transfer, and in this case, we can consider the diffusion of the chemical species to the active side, so to the wash cut, and we consider a 0D model for the wash cut. So then it's important to model also the pollutant species conversion, and so this requires a surface catalytic reaction model. In this case, we use the Langmuir initial good expression to calculate the reaction rates, considering also the effect of species competition to occupy the active sites, including the emission term. So there are several reactions that we included, and they are grouped in reaction schemes. Here I reported the list of the main reactions which we consider, for example, oxidation reaction, reduction reaction, and so on. So then, if we consider a two-way catalyst, so the oxygen storage mechanism is fundamental for the pollutant species conversion, and so this is possible by the continuous oxidation and reduction of cerium. So the reaction rate depends on the local oxidation state of cerium and on the total amount of cerium that is present in the water. So to have a better description of this storage mechanism, two cerium storage sites are considered, the cerium and the post-cerium. One acts at low temperatures and the other at high temperature. So when zeolite material are present at low temperature, is typical the phenomenon of absorption and desorption model of some chemical species that can be, for example, water or unburned hydrocarbon. And to model this phenomena is used the Dubinin-Radushevich model, in which we have absorption when the mass of the absorbed species is lower compared to the equilibrium mass, which is dependent on the local concentration of the chemical species, on the temperature, and also on the saturation pressure. Then, let's pass to the electrical heating model for modeling the electrical heating catalyst. So, in this case, the electrical heating is based on Joule heating effect, and the model resolves the electrical circuit in order to obtain the electrical power distribution. So we do the hypothesis that no magnetic field and zero total volume torque density. So in this way, there is the possibility to compute the electrical potential, then the current density, and finally, the power per unit volume. The last model, last but not least, is the radiative heat transfer model. In particular, if we consider a conjugated transfer during the thermal transient, the radiation plays a very crucial role if we are at a high temperature. So to model the radiation, we use the V1 radiation model with the hypothesis that the fluid is a non-participating medium, and so the radiation is emitted and absorbed at the solid wall. So to consider instead the radiative emission from the catalyst, from the inlet and the outlet surfaces of the catalyst, is considered a proper source term in the radiative transfer equation in the fluid domain. in the catalyst to mimic the radiation obstruction inside the channel of the catalyst itself. A proper limitation function is introduced. At the interface between the fluid and porous media, a modified Marshall boundary condition is applied. Consider that we added a source cell in the related transfer equation of the fluid. So here there is an overview of how these models are linked in OpenFOAM. So we link all the model in a class that is named coupled fluid solid zone. So here there is an example of the dictionary and web parameters of the file. So then pass to the solution algorithm. So we model with a quasi-steady state approach, and we use the time step that is required for the thermal analysis. For this reason, the fluid domain is considered as a quasi-steady state over this time step. Also, the surface chemical reaction is modeled as a quasi-steady state, and we assume that there is no accumulation of reactants and products on the washed-out active sites. Instead, the storage mechanism, which is intrinsically unsteady, requires a proper ordinary differential equation solver, which is operating with time-step supplier. So now let's pass to the experimental validation of the implemented models. So I start proposing to you a substrate thermal validation. So in this test, the goal was to reproduce a heating from cold start condition and then a rapid cooling, keeping a fixed mass flow rate. So in this case, the substrate that was tested is an uncoated metallic substrate. So here there is an overview of the computational domain. Of course, is the region domain, which includes the fluid, scanning, matrix, and another porous region. And the mesh is structured, which NOH topology, and is also coordinated. So the total cell count is around 200,000 purely hexahedral cells. So, sorry. There is a little bit of delay. Vediamo se. No.
It's a video, it's easier to minimize.
Yeah. Okay. Okay, so sorry about the interruption. So here the result of previous test. So in this case, the substrate was instrumented with several thermocouples, which are placed in a different position. And here reported the result at 45 millimeters far from the inlet of the substrate. As it's possible to see, the overall agreement is really good. And we need to consider that in the simulation, we don't model the thermal inertial effect of the thermocouples, which is visible in particular in the external point of the substrate and over the external surface of the candle. And is visible particularly during the heating phase and also during the cooling phase, introducing a time period. So then, to validate the electrical model and also the radiative one, so a test on a simplified exhaust line, which is equipped with an encoded metallic electrical catalyst, is performed, reproducing different heating strategies, which are reported in the table. So the first test was with no airflow. Instead, the second test, there is also a state in which there is an airflow. So in this slide, there is also, for this case, the presentation of the overall computation domain and there is a boom in the region of the electrical catalyst. So, okay. Here the results for the two different test conditions. So also in this case, it's possible to see the overall level of green is pretty good. And one remarkable thing is that if we consider the calculated, so the numerical results without including the radiation model, which is represented by the dotted line, by the dashed line, it's possible to see that during the heating phase, the temperature tends to divert. And so the importance to proper model also the radiativity transfer, which in this type of device is fundamental for having a good representation. So to conclude the part of the pollutant species conversion, so to conclude the part of experimental validation, here is also proposed a part related to the pollutant species conversion, in which we simulate a complete real driving cycle with a 3D simulation. And for sake of clarity, here are reported only the first 150 seconds. So the results refer to a 1.3 liter turbocharged gas engine. And here we have the results in terms of pollutant species molar fraction at the inlet and outlet. So also in this case, the overall agreement is quite good. Here one important thing is that the phase of tuning of the chemical reaction constants is very important because it's different from different type of active workloads. And in this case, we are still working on these results to have a better estimation. So now to conclude, so in this case, a multi-region CFD numerical model has been implemented for the simulation of the after-treatment system. A detailed modeling of the catalyst and all the related physical and chemical properties allows an accurate description of the device. The implemented solution algorithm allows to keep the computational bar low. In this way, there is a possibility to simulate a relatively long time interval. For example, the one regarded for simulating the real driving emission cycle. The CFD models have been validated through the experimental activity. And last but not least, this methodology should be regarded as a promising tool for the development and implementation of the new after-treatment system layout. So thank you for the attention, and I'm available for any question.
Thank you.
Andrea?
I have one. So do you think you need to always run the whole model with all happening in radiation for
There is also the possibility to exclude, for example, the radiative model can be excluded. So the models that are mandatory completely are one, the transfer. For example, we can in the simulation in the test where we have uncoded catalyst, we don't consider chemical caption. And so we have only part of transfer and not transfer.
Yeah, but my question was more like, can you also use the CFD model, the 3D model, implement like reduce order model, like something that would be like here instead of solving, the 2D system?
No, this methodology also works with 1D models. So, for example, for the calculation of the chemical reaction kinetics, we start from a 1D model, so in which we have a discretization only on the x-axis. And in the way the simulation time is low. For example, we start from a simulation that requires 1 week to 3 hours, or even that. And so there is also this possibility.
Right. So in the part medium module, what do you model the heat transfer inside the first medium? And do you also model the pressure flow?
Yeah, regarding the transfer, we consider the convection between the fluid and so maybe I can
Use
go.
the correlations of
Yeah, maybe I can go back. So, nevertheless, so we have a correlation that is based on the Nusselt number. And so we have several correlations that permits to calculate the Nusselt number. In particular, we can keep the Nusselt number constant, cause the flow density unknown in the channel of the substrate. But we have a more refined correlation which consider for the increased reduction in the entrance region of the catalyst.
yeah.
And then it tends to be constant. And so this one is a modified correlation of the photon model.
But in the case of force media properties, the correlation might be very different from our experience when we model heat exchangers. We treat the core as the first medium, depending on the internal structure, the porosity and the fraction, the liquid parts of the solid. So it's the
Again, with the part of the thermal properties. So we consider, for example, in this case, the equivalent thermal properties for media regarding the solid region. Okay. And so we have also a density that takes into consideration that the media is open. So it's not the density of the solid material, solid metal, for example, but taking into consideration also the light fraction.
right.
Okay.
I hope that I can pay up here very into the coffee break. Thanks again to all the speakers.